Well, dear students, hopefully all of you are clear with the positive deviation and negative deviation from Raoult's law, right? And different examples, thermodynamics of solution, ideal solution, real solution, or non-ideal solution. You can say real solution or non-ideal solution, right? So, ideal solution, we can plot vapor pressure versus composition curve for positive deviation and for negative deviation. Graph is almost same with a little difference. So see, this is suppose that this is what vapor pressure. This is vapor pressure of A, and this is vapor pressure of B. So from here to here, this is P naught B, P naught B. This is xb is equal to 1, and here xa is equal to 1, and xb is equal to 0 here. Here xa is equal to 0, and this is p naught a, p naught a, right? See, when your solution is ideal, both the components obeying the Raoult's law. So the ideal vapor pressure of the solution is given like this, right? So this is ideal vapor pressure of the solution, ideal. And what about this real solution showing positive deviation? Positive deviation means this line is not like this straight line. Now this line is like this, right? So this is P solution, P solution, and this is P ideal. So P solution, which is greater than PA plus PB, and this is here, this is P solution, this is P solution, this is equal to PA plus PB, right? So in this way you can show this, and this graph is like this. This is PB ideal, and this is PA ideal, PA ideal, and in the real, this PB is also like this, and like this, right? So this is PA real, and this is PB real. So with the red color I have shown the real behavior, means positive deviation, and with the black ink I have shown the ideal, right? So this is vapor pressure versus composition curve for a solution showing what positive deviation. So such type of solutions, in such type of solution, you get a point at which the vapor pressure is maximum. So sometimes such type of solutions are also said to be maximum vapor pressure type solution, right? Maximum vapor pressure type solution. And negative deviation which are showing, they are said to be minimum vapor pressure type solution. Minimum vapor pressure type solution, right? So there is one point at which the vapor pressure is maximum. After that, this will decrease, and this will decrease. But overall, always more than what the ideal vapor pressure, right? So similar graph you can draw in negative deviation. All are below these ideal lines, right? So if you take negative deviation, so this is P naught A, this is P naught B. Here XB is equal to 1 and XA is equal to 1. P naught A and here P naught B. P naught B, right? So this is what ideal. So the real one is like this, right? So this is P real and this is P ideal. So in this there is one point at which this vapor pressure is minimum. So this is called minimum vapor pressure type solution, right? And so the real one is like this and like this, right? So this is so the negative deviation from Raoult's law, right? So P real, in this case, P real, total P real is less than PA plus PB. And here P ideal, this is equal to PA plus PB, right? And this is actual line, ideal for this is PA and this is for PB. This is actual ideal PA and this is for PB, right? So hopefully all of you are clear with respect to this. This is what vapor pressure versus composition plot. But in the total vapor pressure, at some point we will find a point at which the vapor pressure is minimum, right? The vapor pressure is minimum. Now see how to make the distillation, and here we have the concept of azeotropic mixture. You know, this graph is plotted at the constant pressure, constant temperature. This is at constant temperature, but this is not useful for the fractional distillation purpose, because usually we do the fractional distillation at constant pressure condition, right? So this is vapor pressure versus composition curve for vapor pressure versus composition X. For composition for positive deviation, and this is vapor pressure versus composition for negative deviation. Now see how boiling point versus composition curve is for such type of solutions. So boiling point versus composition. So this is useful for this is useful for the fractional distillation, and from here we can develop the concept of azeotropic mixture. See, I'm not going to waste my time, so I have already selected the picture. So this see, all of you are knowing that what is the relation between boiling point and vapor pressure. So boiling point, boiling point, boiling point boiling point and vapor pressure are inversely related. Vapor pressure, they are inversely related, right? So see what we are getting here in positive deviation. This is what maximum vapor pressure type. So this is the minimum boiling point type. So this is the minimum boiling point of this mixture, of the same mixture what we have taken here. See, here I have taken P naught A is less, so temperature is high, so this point is reverse, and here what, no, not that, because this is I mean it is a different, not, don't compare with this, but only you can compare that this is a, I mean what, positive deviation, and this is negative deviation curve, right? So this is minimum boiling point, maximum vapor pressure or minimum boiling point. So this is the minimum boiling point of this solution. And if you see, this point is very unique for this mixture. This point, I can name this point capital A here. So this point, liquid, see, this is the liquid phase and this is the vapor phase, and both were mixed, both were merged, and here this point is A dash, you can take. So A and A dash, A and A dash are the point composition corresponding to this point. So if you draw a perpendicular, here we are getting this, and here if we draw the perpendicular here, and this is different for different I mean substances. So it 0.4.4243, 0.45 we can take, 0.43 we can take here, 0.43, right? And here it is 0.6 we can take. So this composition with respect to this merge point at which this liquid liquid and vapor are merged together, the composition, this point is called azeotropic mixture. If you take the mixture at this point, this composition, so for A it is x1 is 0.43, x1 is equal to 0.43 I have taken, so x2 is equal to 1 minus 0.43. So at this composition, this system forms the azeotropic mixture. What is the meaning of this? The meaning of this is that the composition of liquid phase and vapor phase is same, because you know liquid and vapors are merged together. But beyond this point, if you take any point, the liquid composition is different from the vapor composition. All of you are getting my point or not? So azeotropic point or azeotropic mixture is a unique for a given pair of volatile liquids, right? So this point is unique for given mixture, right? And for A dash, this x1 is equal to 0.6, so x2 is equal to 0.4. So this system forms azeotropic mixture with this composition. So this composition is fixed. Whenever you are mix x1 and x2 in this ratio and bring the temperature corresponding to this point, you can take this, and if you bring the system at this temperature, so at this temperature, this with this composition, the liquid phase mole fraction and vapor phase, suppose that question is asked, okay, tell me what is the vapor phase composition here. So vapor phase composition is here, y1 is equal to 0.6 and y2 is also equal to 0.4, right? So at this point, the liquid and vapor phase composition becomes same. Means you cannot and temperature is same for both. So you can say whole mixture will boil at the same temperature and condense at the same temperature, and therefore you cannot separate them by fractional distillation. And here for A also the same argument. So this A and A point, A dash point, they are known as azeotropic right? Azeotropic points. Azeotropic point. So once a system forms azeotropic mixture, it cannot be further separated by fractional distillation, right? Now all these terms, what it is clear to all of you. This is liquid phase, this is vapor phase. So this composition is the liquid phase composition, then corresponding vapor phase composition is at the point B. So this is the vapor phase composition. So if this is x1 is richer in liquid, then x2 is richer in vapor. So and this B to C line, again condensation line, vapor to liquid, you are moving from vapor to liquid. See, this is liquid, this is vapor. So B to C, this is condensation, and C, this is again evaporation. From C to D, you are moving from liquid to vapor, so the vaporization, this is condensation. So this line represents basically fractional distillation. And similarly here, but once it will form this composition, you cannot further separate them until or unless you are not changing the composition. Once you alter the composition, again you will distill. So azeotropic mixture is also known as constant boiling mixture. So azeotropic mixture also known as constant boiling, boiling mixture, right? And have same composition in liquid as well as in vapor phase. See, both the lines are merged here. After that, they are further separated. So beyond this means before this you can separate, after this you can separate. But don't think how to get this composition. We can change by altering, by adding some liquid, right? Some composition we can change. We can adopt this state at this state as well. So, but at this point you cannot separate the components by fractional distillation. So you can write here, once a mixture forms azeotropic condition, once solution forms azeotropic state, it cannot be further separated by fractional distillation method. Right, so this is all about azeotropic mixture. You know, when two liquids are mixed and this state will exist, then it is called azeotropic mixture or constant boiling mixture. When two solids were mixed, and for solids this point also come. When two different solids, means suppose that you have mixed copper and zinc, both have different melting point, but in a fixed proportion, in the fixed ratio, molar ratio, they means zinc and copper will melt at same temperature and freeze at same temperature. So for solids also this situation exists. You know, for solids, if this situation exists, then that mixture is called eutectic mixture. What is called eutectic, EUTIC, eutectic mixture, right? But it is not in your syllabus. So when two liquids are mixed in a and having real behavior, or definitely all of you are knowing that every mixture is real behavior, showing real behavior. You won't get perfect ideal behavior from anyone. So in every liquid mixture, if one liquid has some boiling point T1, other liquid have boiling point T2, when both are mixed, right, at some particular composition, both were boiled at same temperature and at condensed at same temperature, and this is known as what? Azeotropic mixture. The composition corresponding to that is called azeotropic mixture. And one more feature is also that this vapor and liquid merge together in that particular composition, means what? Liquid and vapor both have same mole fractions, right? Good. So this is all about positive and negative deviations from Raoult's law. Okay. So now we will move the case third. This is the second case. Now I am moving to the case third. What is the case 3? Case 3 is A is volatile. A means solvent. It is volatile. volatile, right? And B is solute, and it is non-volatile. So now we want to study uh, the effect on vapor pressure when a non-volatile solute is mixed to the solution. I mix to the volatile solvent, right? So in this situation, when non-volatile solute is mixed, non-volatile solute is mixed, right? And right. So now tell me, which molecule will go in the vapor phase? Only the volatile component molecule will go in the vapor phase. So if you compare this, with the pure solvent, suppose that we have taken here pure solvent, and in the vapor phase only A molecule, here is also only A molecule. B is non-volatile, so B will not be there in the vapor phase. So and both were kept at the same temperature. So in this case, the vapor pressure of A is known as P naught A, because this is what pure. And how to calculate this? You can very easily calculate moles of A in vapor phase into RT by V. Simple formula. Equation of state, right? P naught A. So by using this formula, you can what calculate? This is pure. Now in this mixture, what is vapor pressure of A? Now this is what? PA. So PA, why I am writing PA here? Because you know this is not pure. Some effect of this B must be there. See, this is pure solvent. This is pure solvent. Pure solvent. And this is solution having non-volatile solutes. So the effect of B we have to consider here. So this PA means vapor pressure of solution vapor pressure of A in solution, and this P naught A is the vapor pressure of A in pure state, right? So is this PA is equal to P naught A? The answer is no. PA is not equal to P naught A, right? PA is not equal to P naught A, and what is the relation? The relation is that PA is less than P naught A. right? P naught A. So what is P solution? Can you write here? What is P solution? The P solution is equal to PA PA, because B is not in the vapor phase, only A in the vapor phase, and you can use Raoult's law here also. See, Raoult's law here also applicable, because for volatile component A is volatile, so you can write PA is equal to P naught A X A, simply that previous formula. So you can write here A is equal to P naught A X A as per the Raoult's law. So this is the P solution, you can see. So this is the Raoult's law. This is Raoult's another law. Raoult's second law, right? This is also called Raoult's law. So P solution is equal to P naught A into XA. Now it is clear to everybody. And this PA or P solution is definitely less than the vapor pressure of this. Okay, now we can change some useful term. P solution is equal to, we can write P naught A 1 minus what, XB. We can write XA is equal to, XA plus XB is equal to 1. So XA is equal to 1 minus XB. So we can write here P naught B minus P naught B into XB. Right? So you can write here P naught B, sorry, P naught A, not P naught B. P naught A minus P solution is equal to P naught A XB. So this is very important relation. This is equation 2, and you can write here P naught A. This is the vapor pressure of pure at the same temperature. T should be same. P naught A minus P solution is known as lowering in vapor pressure. Lowering in vapor pressure, right? This is very important term for you. Lowering in vapor pressure means, suppose that the number of molecules in pure state are reaching here, suppose that X molecules of A are reaching in the vapor phase in absence of B. So when we are mixing B and the behavior of A and B is ideal, means everything is perfect to make a ideal solution. Until then, means there is no interaction, you can assume there is perfect situation of ideal mixture. Even then the moles of A in vapor phase are reduced. So sometime many people explaining, many instructor, many teachers are explaining this like this, that some of molecules of B will occupy to the surface, so the surface area will reduce, therefore vapor pressure reduce. But the answer is no. This is bogus explanation. right from beginning we are always here to that vapor pressure mainly depends on temperature, so temperature is same, and one or two other factors like presence of some inert gas or some pressurization of the solution, and this is not the case here. So why nowhere we have studied this vapor pressure depends on the surface area? Hmm? If there is no interaction between A and B, so there will be no chance of the reduction of this vapor pressure or reduction in the number of molecules of A in the vapor phase. There is no chance. So what is the correct explanation why this here the moles of A are less in vapor phase? Means in presence of a non-volatile solute the vapor pressure is decreases. So this is the conclusion that presence of this non-volatile solute decreases the number of molecules in vapor phase, so vapor pressure decreases. Means if we put some non-volatile solute in the volatile solvent, the vapor pressure will decrease. So this is the effect of addition of solute. So what is the correct explanation why this is reducing? So I will explain. Wait few minutes. So presence of, this is a very important conclusion, presence of non-volatile solute decreases the vapor pressure of solution, or you can say solvent, volatile solvent solution, right? So this presence of non-volatile solute will decrease the vapor pressure of solution. Again one question arises, why? Because we know temperature is same, and we are knowing that vapor pressure depends on temperature and presence of some inert gas or some external factor like pressurization, and none of the other any factor. So what should be the best explanation of this? See, the best explanation is basically based on the thermodynamics. Explanation. What is the explanation of this? See, when we are comparing two systems, suppose that here we have pure solvent, so you are taking and here equilibrium is there, and here some moles are in the vapor phase. So this is pure, and T is same for both. Here you have same quantity, exactly same quantity you are taking for the solvent. Here also equilibrium, but this time in the vapor phase molecules are reduced. But this time in the solution B is also there, right? So here A plus B, A plus B, A plus B. B is non-volatile, right? And this T is same, and this is solution, right? So in thermodynamics, all of you gone through this entropy. So the best explanation of this, why vapor pressure reduces in presence of a non-volatile solute, is the based on entropy, right? In your book, what is given, I don't know, but this is the ultimate molecular explanation of this phenomenon. You know, what is the natural direction of flow of process? The natural direction is from low entropy to high entropy. This is the spontaneous direction of any process. So, you know, this liquid, I mean A, this is only A here. So, this A has some entropy and a vapor of A has more entropy. So this is the reason why this A is converted into vapor. So here entropy, let it be S1 entropy. So now tell me, when we talk about the entropy of mixing here, so in the solution what you are getting, entropy of mixing increasing or decreasing? Obviously increasing. So because the number of molecules are increasing, you know what is entropy? Entropy is the measurement of randomness. So you are increasing the number of molecules, A and B you are taking, so the possible orientation of different molecules is increases, randomness increases. So if you increase the randomness, if you increase the number of molecules in any system, randomness increases undoubtedly, exceptionally. So here this S2 is the entropy of this liquid system. So S2 is entropy of solution, and this is much larger than S1, entropy of pure solvent. So what is the effect? The natural direction is from low entropy to high entropy. See, this is the from low entropy to high entropy. High entropy. This is the natural direction of flow of any process. Natural direction of any process. So here evaporation is a process. So the natural direction of the process is from low entropy liquid to high entropy. So now tell me, when the entropy of this is increases, so from more to further movement in the further higher entropy, this tendency will reduce. See, you know, for at given temperature, entropy is what? Fixed. So because it depends on temperature. So here the pure solvent has less entropy and this has more entropy. So since the solution has more entropy, so from more to further higher, this tendency will decrease compared to from lower to higher. So this is the reason why, if already entropy of the system is on the higher side, so from higher to further higher, this tendency will decrease, right? So the correct explanation of this is that solution has more entropy. Solution has more entropy. More entropy than pure solvent. Pure solvent. Therefore, the relative tendency the relative tendency to further increase in entropy will decrease. Right? Thus, solution has lower vapor pressure than pure solvent at given temperature, at same temperature. If solute is non-volatile, right? So this is the concept. So now it is clear that this lowering in vapor pressure is due to the increase in the entropy of the solution. This is due to the increase in the entropy of the solution. This will, put, bar, or you can say check on the relative escaping tendency, means it decreases the chemical potential basically. So when entropy will increase, chemical potential will decrease. It is well known, and we have already studied this. Del G by del N is equal to del T. Del G by del T is equal to minus of S. So if S will increase, chemical potential will decrease. Chemical potential will decrease means relative tendency will decrease. So already we have discussed all these relations with entropy and chemical potential, because you know how much this liquid will go into vapor phase. This will determine by the chemical potential, because you know at equilibrium the chemical potential of this vapor is equal to the chemical potential of this liquid. So here also chemical potential of this vapor is equal to the chemical potential of this liquid. So this is equal. This is always equal. Otherwise there is no equilibrium. So here once the chemical potential will decrease, because entropy will increase here, right? So if you see the initial relations we have in the beginning of this. See, chemical potential with respect to what temperature, this is equal to minus of S. So this, if this will increase, this entropy will increase, chemical potential will see here as per the third law, entropy if greater than 0. So chemical potential will what? Decrease. So chemical potential if decreases, so the relative tendency to convert in the vapor phase, that will what? Decreases. So here this chemical potential C dash and here nu. So if you want, you can compare that chemical potential of this liquid is what? More than the chemical potential of this, right? So in terms of entropy you can write like this, and in terms of chemical potential you can write mu of liquid is more than mu dash of this solution, right? So obviously if chemical potential is more, chemical potential means escaping tendency. What I have sometime I have referred this as escaping tendency. So if chemical potential of this is more and this is less, so this has relatively more tendency to go into the vapor phase compared to this of the same component. So see how the behavior of this material or our system is controlled by a single property and known as Gibbs energy per mole, right? So in terms of entropy, either you want to explain, or in terms of chemical potential, whatsoever you like, you can explain, right? Okay. So this is what the explanation of this lowering in vapor pressure. So now from equation 2, again I take up this equation 2, P naught A minus P solution by is equal to P naught A into XB, where XB are the mole fraction of non-volatile solute. So from this equation 2, we can write P naught A minus P solution by P naught A is equal to, you can write delta P, this is the lowering in vapor pressure, divided by P naught A. This is equal to XB, and this is equation 3 or 4. You know what is this term is called? This term delta P by P naught A is called relative lowering in vapor pressure. Relative lowering in vapor pressure. And this is equal to mole fraction of non-volatile solute. You know, this is the statement of second law of Raoult's. So the relative lowering in vapor pressure, relative lowering in vapor pressure, RLVP, we can abbreviate this, is equal to the mole fraction of non-volatile solute. What does it means? It means more you add this non-volatile solute, more is the reduction in the vapor pressure with respect to the pure. Reduction in vapor pressure with respect to the pure. Not only reduction, more will be the reduction in vapor pressure with respect to the pure. So this is called Raoult's law, Raoult's second law. So you can say the relative lowering in vapor pressure, the relative lowering in vapor pressure is equal to the mole fraction of non-volatile solute, right? And this is the second Raoult's law. Okay, so hopefully all of you are clear that what is Raoult's second law. What is the validity of this equation? What is the limitation of this equation? The limitation of this equation is the solute should be non-volatile, solute should be molecular state of solute and solvent remains same before and after mixing, means there is no secondary interaction between solute and solvent molecule. Temperature of the experiment is what? Constant, and this solution should be sufficiently dilute. Means if you take a very concentrated solution, so this law will not hold. This equality will not hold basically. Law is not hold means equality will not hold. So what is the limitation? Limitation of this law. Limitation of equation 4. Equation 4 is, first point, solute should be non-volatile and non-electrolyte. Non-electrolyte. Right. Second point is molecular state. You know why I am writing this point? You know, not every electrolyte, some non-electrolytic substances also may dimerize, trimerize after mixing. So molecular state of solute and solvent, both of solute and solvent should be same before and after mixing. Before and after mixing. Before and after mixing. Right. Now, third point is temperature should be constant. T should be constant. Fourth point is solute should be, solution should be sufficiently dilute. Solution should be dilute. That is ideal, right? Dilute means ideal. So these are the limitations for this equation, right? Now we can see what is the application of this rule, right? So application So the application is the determination of molar mass of solute, right? So determination of molar mass of solute. So how to determine? C, delta P by P naught A is equal to XB, and now you can write XB is equal to NB by Na plus NB. And now use this point, dilute solution means you can write NB are less than Na, right? So you can write here this is equal to NB by Na, right? And this on this NB you can change this. This is WB by MB into Na, right? So if we do this, take a known quantity, known amount of this solute in the given quantity of solvent, and if we measure this relative lowering in vapor pressure, so this is known, and this left hand side term is known, so we can calculate this MB, right? So this is delta P by P naught A, right? So you can determine the molar mass of molar mass of this solute, right? So this is the application of this Raoult's law, right? So hopefully all of you are clear with this relative lowering in vapor pressure. This is the case 3, right? Case 3, when solute is non-volatile and a solvent is volatile, and you know this is very useful case, and the rest of the chapter will is based on this concept only. So now we have started the second part of this chapter, and hopefully in the next 2-3 lectures your this chapter will complete, right?